So we now turn to looking at triangles in hyperbolic space. We actually briefly already saw ideal triangles. We'll see ideal and not so ideal triangles now. They're both very important for constructions in hyperbolic geometry, and we'll also mark our transition to geometric group theory. So here are a couple of examples. There are angles alpha, beta, and gamma for the triangles. Well, what do we know about the angles? First thing we know is that alpha, beta, gamma are greater than or equal to 0, but they may be equal to 0, unlike Euclidean space. In this picture, these two are equal to 0. So beta is 0, gamma is 0. And the reason for this is, as I mentioned briefly earlier, if we look at the tangent lines to the circles at this point, both these circles are perpendicular to that, and so they must be tangent to each other. So the second thing we know is that an angle equals 0 if and only if the corresponding vertex is ideal. So this is the first thing we know. And the second thing we'll see, we're just taking a simple picture. Here we have these sort of curved lines, which are chords, arcs of circles. And what I've drawn are the straight lines, which is the Euclidean one. Well, I mean, it's quite clear, and you can just check from the definitions with a little care, that the hyperbolic angle, this, is less than Euclidean angle. And the Euclidean angles add up to pi. So alpha plus beta plus gamma is strictly less than pi. In fact, at the extreme for ideal, they're all 0. So it lies between 0 and pi. So each of them is a non-negative number, and they add up to pi. So this is what we know. Well, the first main result here is about hyperbolic geometry, triangles in hyperbolic geometry, is that suppose we are given alpha, beta, gamma greater than or equal to 0, pi minus, okay, I'll write it that way, pi minus alpha plus beta plus gamma is also greater than or strictly greater than 0, then there exists triangle, okay, I'll call it delta alpha beta gamma, unique up to congruence, with these angles, with angles alpha, beta and gamma. Now there are several remarkable things. Of course, in Euclidean space, angles don't determine a triangle up to congruence. They determine it only up to similarity. Yeah, so that is a major difference. Otherwise, we have a statement similar to the Euclidean one. So once you know the angles, you know the triangle. And any angle subject to only the restrictions we already saw is permissible. Any triple of angles is permissible. So let's see how this goes. So by symmetry, we can take, so we look for a triangle PQR. And here's already a picture. Okay, and without loss of generality, let's say P equals 1 and Q belongs to the imaginary axis IR. Q with P equals I. So I'm using the upper half plane model. Okay, so this is the point I, and I've drawn it. So I've drawn an angle alpha here. Okay, so this is the angle alpha here, where is P, and we have a vertical line passing through that. Well, what happened if I took, so I take a point Q. Let's first start with a point Q here, which is Q minus 1, and take an angle beta. Now in the Euclidean situation, what happens always is that if we have a line and we have two given angles on it, okay, alpha and beta, now these eventually meet at a point, okay, so these meet if and only if alpha plus beta is strictly less than pi. So that's sort of extension of the parallel postulate. But in hyperbolic geometry, you see that's not true. Here alpha plus beta is visibly less than pi. However, if Q minus 1 is very far away, well, then what happens to So we get a little circle here. I mean, this is supposed to be a semicircle. This is a hyperbolic geodesic, with these being right angles. They don't look that way. And if Q is very far away, well, they just don't meet. They go and each of the geodesics goes and hits infinity before they meet each other. So in this case, there is no triangle. Okay, so that's not very visible. So in this case, there's no triangle. Well, if we take Q closer and closer, at some particular point Q0, we get R is ideal vertex. So these meet in some sense, they meet at infinity. So that we'll get an angle which is 0 here. Gamma is 0. Okay. And now suppose we start moving from Q0 to P. So what have we seen here? That so beyond Q0, there is no triangle. Okay. So by construction we have fixed alpha, beta and trying to figure out what gammas we get. Okay. In the Euclidean case we get a unique gamma. Okay, that's always pi minus alpha plus beta. Okay. At Q equals Q0, gamma equals 0. And what happens at the other end? Well, at the other end, this is a fact which you can see in many ways, but at the other end, when we are here, okay, somewhere some Q here, what happens as Q approaches P? Well, triangle approaches Euclidean, which means that gamma goes to pi minus alpha plus beta, okay, which is the Euclidean situation. So gamma starts off with 0 at Q minus 1, and as you approach here, it hits the Euclidean situation. Okay. So this equation incidentally can be written as pi minus alpha plus beta is strictly greater than 0. Okay. And then we also have, of course, gamma. So this is supposed to be gamma. So as Q approaches the triangle, gamma approaches pi minus alpha plus beta, okay, which is the corresponding Euclidean angle. And in fact, as Q goes from Q0 to P, gamma of Q is monotone. Now this is a fact of a sort which is very important in hyperbolic geometry. Lots of convexity properties and so on come from these. But I'm not going to prove these things. You should look at the calculation. So what happens to the angle gamma? If I take any intermediate position, you see it's not difficult to see that we'll get another triangle. If I took gamma somewhere here, for example, again making the angle beta. Okay, so if I took Q here, okay, I would get some angle, and this angle I can call gamma of Q. Fine. So this is the situation we have. So what happens is that at some point you end up with 0, and as you approach P you end up with a Euclidean angle, and in fact you steadily increase between the two. So then given any value of gamma, we are given gamma which is greater than or equal to 0, and gamma is oh sorry, I wrote this equation wrong. I want to take gamma to the other side. So gamma is less than pi minus alpha plus beta, and greater than or equal to 0 is in the other case. So gamma takes the value 0 and it approaches pi minus alpha plus beta. So it takes every value in between exactly once. And our choices of putting the P at the point I and the axis as the vertical axis are exactly the choices that fix the symmetry. So this is the first. So from this we see that hyperbolic triangles are exactly described by their angles. Okay, now we want to see a couple of more things about the triangles. So I'll state a theorem which follows by calculation. So we have a triangle alpha beta. What is its area? Well, here's a remarkable fact. The area of triangle is pi minus alpha plus beta plus gamma. Well, I mean, there existing a formula is not very remarkable. What is remarkable about this is for all triangles, okay, the area of whatever triangle is less than or equal to, strictly less than, less than or equal to pi. This is very remarkable because when you can't, in Euclidean space, of course, you can make a triangle as big as you like. So this is saying that you have something absurd, namely that all triangles have area at most pi. Well, pi in fact turns out to be area of ideal triangle. Okay, fine. So now what we have seen is ideal triangle is unique. So I'll just make a remark here. Easy to see that area of delta is less than or equal to area of ideal triangle. Okay, and we had already seen that there's a unique ideal triangle. So this is a well-defined quantity. So this is a unique. There's a single number which is this. But you would expect that number to be infinity. Okay, so I will just justify. I won't make this calculation. Why area of ideal triangle less than infinity? This is what we'll try to see in a picture. Let's turn to our upper half plane and let's take a triangle. It has one side here, a second side here, and a third side here. Well, I can take a sort of barycenter. This point in this upper half plane, it doesn't look much like that. Okay, let's draw it here. The triangle is symmetric, so that we have seen. So there's a point which is equidistant from three sides. So all you need to show is that the area here is finite. Okay, this area finite. Okay, but to show that, we'll instead cut off here. Okay, and then show that this area is finite. Well, what is this area? Okay, so we want to show this area. Let me just clarify here. This point here is I, okay, which is 1 times I. I'll write it as 1 times I. So this is actually, that is the y coordinate is 1, and this goes off to infinity. So this point has to be just 1, and this point has to be minus 1. Okay, so what is this area? This is the integral where x goes from minus 1 to 1 and y goes from 1 to infinity. Okay, I could have put them in the other direction, perhaps I will. So let's turn this around instead. Y goes from 1 to infinity, and then x goes from minus 1 to 1. Okay, of what is our scaling factor? It's 1 over y squared. Okay, that's because hyperbolic metric scales by 1 over y, so area scales by square of the length times dx dy. Dx is the inner limit. Okay, this is of course integral of 2 by y squared dy from 1 to infinity, which is 2. Well, 2 happens to be less than infinity. Well, of course, this is only the area of one piece. Okay, so this is an upper bound for about for the area of this part. Okay, I got slightly worried because 2 is not bigger than pi, but of course we have 3 such cusps. So what we get from this calculation is that hyperbolic area is less than 6, and of course 6 is an upper bound for pi, which is the true value. So what I was illustrating is that we want to see that the area is finite, and this is the qualitative property that's extremely important. So let's conclude something from this. This will be our final conclusion about triangles in this segment, and which will let us transition to geometric group theory, which is thin triangles. You see, what we have is we have ideal triangles that have infinite diameter. We saw geodesics have infinite length, so they have infinite diameter. Or if we take a real triangle, they have as large a diameter as you want. So large diameter, and we have small area, or rather, let's be accurate, bounded area. The area need not be small, but it's bounded area. Well, how is this even possible? Well, it's possible if thin. The only way you can have something, well, so let me draw a picture of something with a very large diameter but very small area. Well, it has to be very thin. Actually, it can have a little bulge here. So thin for most of the whatever object we are talking about. So having a large diameter but bounded area means that you're mostly very thin. You can have a little fat part which captures some of the area. Okay, so here's the thin triangle theorem. Okay, so there exists delta greater than 0, and this is, let me emphasize, universal. It doesn't depend on anything. It just depends on hyperbolic space, nothing at all. It's a universal constant as far as hyperbolic space is concerned. There exists delta greater than 0 such that if L1, L2, L3 are sides of a triangle, then L1 is contained in the delta neighborhood of L2 union L3. Okay, so what this is saying is that I have L1, I have L2, and I have L3. This is how a typical triangle looks. Given any point here, a point here is close to, so let me call this side L1. A point here is close to L1. A point here is close to L2. A point here is close to actually both of them. But any point is a distance at most delta from one of the other sides. Again, it's absurd in a Euclidean case. I mean, in a Euclidean triangle, if the triangle is big, the midpoint here is actually quite far from both these sides. Okay, it could be arbitrarily far by just scaling up. So this says that any side is close to it. Okay, so a sketch of the proof, a little hyperbolic geometry fact concerning areas I'm not going to prove now, but we'll return to areas when we look at geometric group theory. So let delta greater than 0, what is this constant, be such that the semicircle of radius delta has area greater than pi. Okay, so what this, so again the semicircle is correct. That is to say, there is a unique, so take a geodesic, take a point on it, and you look at this region. Okay, so this, suppose this is delta, what you require, suppose this is delta, what you require is the area of this semicircle is greater than pi. In fact, hyperbolic areas are greater than the corresponding Euclidean areas. So if pi delta squared by 2 is greater than pi, it's enough. Okay, so in fact we have something quite explicit, which is delta is greater than 1. By the way, pi is replaced by some other element, you can take a larger thing. So this depends only on the qualitative fact of area being bounded. So what is the argument? So a semicircle about some point P in L1 must intersect L2 or L3. Okay, so let me take a final picture to show you this. We'll look at a Euclidean picture where this is false. So in a Euclidean picture here, let's take a point P here, and let's take a semicircle of radius delta. Okay, and this doesn't intersect either of the other sides. Okay, so these are of course the sides L1, L2, L3. So what we know is area of triangle is greater than area of semicircle, which is greater than pi. So okay, inequality is okay. So what happens, what do we see from this? On the other hand, in the hyperbolic case, this cannot happen, and the only way in which you can rule this out is because if I take any point P and I take a semicircle of radius delta, it has to go and hit this side. Okay, so this concludes, so from this we conclude that any point on a side is close to one side or the other. So I'll leave you with the last picture. So this thin triangle sort of looks like a triangle on a tree, and that is the picture to keep in mind. Okay, so it's, you think of a tree, which is this simple tree here, and there a triangle is just a rather degenerate object which goes up like this and comes like this and comes like this. Okay, well, a hyperbolic triangle is not that degenerate, but this is the rough model. This is thin, this is very, very thin.